Hello everyone, my name is Muhammad Alfian and today I will be presenting a strategic AI implementation framework for the National Smart Grid Initiative. This presentation outlines a high-performance, robust and ethical system designed to modernize our national power infrastructure. Our national grid faces two critical challenges today. First, outdated forecasting methods can handle the complex, non-linear demands of a modern economy or the variability of renewable energy sources like wind and solar. Second, the physical infrastructure inspection is slow, costly, and also hazardous. To solve this, I am proposing a dual system architecture. This framework separates the workload into two specialized pipelines. The Pipeline 1 uses historical data for demand forecasting, and Pipeline 2 utilizes real-time drone videos feed for infrastructure fault detection. Let's look at the algorithms powering this pipeline. Okay, for Pipeline 1, energy demand forecasting, we had to choose between a traditional linear regression model and deep learning approach using the long short-term memory or LSTM networks. We selected the LSTM for two main reasons. First, linear regression assumes a linear relationship between the variables. However, real-world energy consumption is highly nonlinear and complex, so the linear assumption simply does not hold in grid operations. Second, linear regression ignores the sequence of the data. Energy demand is driven by the time and daily cycles, weekly patterns, and seasons. LSTM networks are specifically architected for this. They utilize a mechanism called the forget gate, which allows the model to learn long-term dependency while ignoring irrelevant past data, such as a holiday spike from the last week. So this makes LSTM the superior choice for preventing breakouts and optimizing resource allocation. Moving to pipeline 2, we need to detect a fault like a crack insulator using drones. So the critical constraint here is speed. We compare the standard two-stage detectors like RCNN against the one-stage detector YOLO, you only look once. So a drone inspecting power lines flies at approximately 60 km per hour, covering nearly 70 meters every second. So a standard RCNN is accurate but computationally heavy and slow. If the model lags, we risk missing a fault entirely. So in contrast, YOLO processes the entire image in a single pass. Recent benchmarks show YOLO V4 achieving over 100 frames per second with high accuracy. And this real-time processing capability makes a YOLO the only viable option for high-speed drone inspection. However, high-performance models often fail when moving from the lab to the field. This is usually due to overfitting, where the model memorizes the training data rather than learning generalized features. We detect this by monitoring loss curve. If training loss goes down but validation loss goes up, the model is failing to generalize. To mitigate this, we employ a rigorous data augmentation strategy. We cannot wait for rare weather conditions to happen naturally, so we simulate them. We use a geometric transformation like a rotation, shearing to ensure the drone recognizes towers from any flight angle. We also use a photometric transformation, adjusting brightness and injecting noise to simulate different times of day, cloud cover or sensor grain. So this ensures our AI remains robust in rain, fog, or direct sunlight. We must address the ethics of deployment. The most significant risk is a false positive, where the AI incorrectly triggers a power shutdown in a critical area, like a hospital. For example, in this scenario, algorithm incorrectly predicts a surge. Then the autonomous power cut to a critical zone, for example the hospital, and the consequence is the disruption of a life support system. So AI is actually a decision support system, not an autonomous moral agent. To prevent this, we implement a human-in-the-loop (HITL) governance workflow. The green zone for the low-risk rural areas with high detection confidence, the system can act autonomously. Then, the yellow zone. This is for moderate risk. The system acts as a decision support tool, alerting a human operator to verify the fault before taking action. And then the red zone for the critical infrastructure, like hospitals. Autonomous cutoff is hard-coded as a disable, even with 99% confidence. The human supervisor must authorize any disruption. This ensures safety and accountability. In conclusion, this framework offers a comprehensive path forward. By utilizing the LSTM for accurate forecasting and YOLO for high-speed fault detection, we maximizes efficiency. By applying a data augmentation, we ensure reliability in the real world, and strictly enforcing human-in-the-loop protocols. We ensure that our pursuit of automation never compromises public safety. This strategy transforms our grid into a secure, intelligent, and resilient national asset. Thank you.